So let's look at this problem. This is, you have a stochastic process x of t, except that the t is replaced by psi i's are positive random variables. So you could clearly see that this is going to represent, so if you define ti to be, or tn rather, to be summation psi I equal to 1 through nt, this variable, then we could write this as yn as x of ti. So you can see we are sampling randomly here. The randomness was dictated by these random variables. So the question now is, you are generating a randomly sampled random process, and we want to find out its first order and second order characteristics. So if x of t is 0 mean, you can clearly see that y of t is 0 mean. So what will be more interesting is so t1 is going to be psi 1, right? T1 is psi 1. Now so this is psi 1. Depending on psi 2, t2 is, so if psi 2 is small, so t2 is going, if this is psi 2, then this will be t2. And if this is psi 3, yeah, then this is going to be t3. So that's what I mean by the time instants are dictated by random sampling, right? So to find out the autocorrelation function ryy m comma n is going to be expected value of ym yn let's say n is greater than m, so this is going to be expected value of x of summation psi I equal to 1 through m multiplied by x of psi I equal to 1 through n. And once again, because there are several random variables here, we'll use the conditional principle. So this is expected because expected value of something can be written as expected value of the quantity inside conditioned on some random variable. So we will of course condition it on these psi i's. So this now reads let's say expected value of xi I going from 1 through m multiplied by x of psi I from 1 through n conditioned on all these psi i's. And these psi i's are of course independent among themselves, and also of course independent of x. So given the psi i's, now you have the only randomness is due to x, and let's say x is given to be x of t is a Whiteson stationary process. X of t is to start with is Whiteson stationary with autocorrelation function rxx tau. Tau is of course t1 minus t2. So this is our t1. This is our t1 minus t2 or t2 minus t1. Let me take it to be t2 minus t1, the difference of the indices. So this which in this case now simplifies to, so expected value is going to be rxx, t2 minus t1 is going to be summation psi I going from m plus 1 through n. But to make a further simplification, we can try to express the rxx in terms of its power spectrum. If you recall, rxx tau is going to be is 1 over 2 pi minus infinity to inverse transform of its power spectrum. So this is e raised to j omega tau d omega. So which is what I am going to substitute it here. Consequently, y turns out to be 1 over 2 pi expected value of sxx omega e to the power j omega tau. So tau is going to be this quantity. So notice that, of course, this expectation is now with respect to all these psi i's. And the argument here is that given the psi i's, the inside expectation is going to be just this, and then it's because it's going to be rxx t2 minus t1, which is what we have here. So this is going to be psi I equal to m plus 1 through n d omega. But notice that this expectation is going to hit here. So this is going to be 1 over 2 pi minus infinity to plus infinity sxx omega expected value of e raised to j omega sigma psi I equal to m plus 1 through n. But this is now, notice that this is the characteristic product of the characteristic functions. But on the other hand, in other words, this quantity here, this summation of course can be written as product I equal to m plus 1 through n e raised to j omega psi i's. But these are all independent random variables. Consequently, their expected value is the product of the expected values, and each of them represent the characteristic function. Let's say they are all identical, then it is simply simplifies to so if this is the characteristic function of Ci to the power n minus m, so many of them d omega. So the point is, now if you look at this expression, we started with here m comma n. If you look here, this is not a function of, this is only a function of omega, this is a function of omega. N and m appear here as n minus m, saying that the process y of t is indeed White's and stationary also. So here is the bottom line. If you sample a process randomly, and if these random quantities are all independent, then if the original process is White's and stationary, then the sampled process is also White's and stationary. Now we can make further simplifications, so that's established. So this of course says that yn is White's and stationary, provided the random samples are sampling is random. Random and where the and independent. In other words, the psi i's are independent. Now you could use specific distributions. For example, if you say that the psi i's are geometric random variables, then we could find the characteristic function for the geometric random variable. Or it can also, if the psi i's are geometric, then this whole quantity is negative binomial, if you recall the properties of the random variables. And then we could find out the characteristic function for the negative binomial random variable. So if you, for example, let's say psi i's are geometric with parameter p, then this random variable z, which is summation psi I equal to m through n, is negative binomial with the parameter n minus m comma p, and consequently it's a characteristic function. So this whole thing we could call to be phi of z of omega, right? This whole thing. So phi z of omega is going to be summation, the probability density function of the negative binomial multiplied by e raised to j omega. So that's going to be n minus m plus k minus 1 comma k p to the power n minus 1, the parameter q to the power k e raised to j k omega. So if you substitute this into this expression, so remember this is the ryy n minus m. So ryy n minus m, because it's also weights and stationary. So ryy n minus m turns out to be 1 over 2 pi integral minus infinity to plus infinity sxx omega. Then you substitute this expression here, which is all this constant. So constant n plus m plus k minus 1 k, and here the summation is from k equal to 0 through infinity. So k equal to 0 through infinity, p to the power n minus m, q to the power k e raised to j k omega d omega. But notice that the constant comes outside, so this of course ultimately simplifies to summation k equal to 0 through infinity n minus m plus k minus 1 choose k, p to the power n minus m, q to the power k. Then the rest of the term is integral sxx omega e raised to jk omega d omega. That's going to be the autocorrelation function of x evaluated at k. So if you want, you can also write this in terms of the autocorrelation function. But mind you, this is the general expression. So here we have already established that yn is weights and stationary. In particular, if the sampling is according to geometric, then we can, as an illustration, we can further simplify this in this manner. Or you can also further simplify the ryy or n minus 1 in terms of the autocorrelation function of x and the probability density function of this random variable z.